I'm going to analyze the relationship between features and the target variable using partial dependence plots, PDPs. PDPs show how much each feature contributes to the model's predictions. This is the core of the problem. I need to interpret the meaning of the positive and flat PDPs for each feature to determine what the plots say about their predictive power. I'll break down the problem into steps to make it easier to solve. I will carefully analyze the partial dependence plots individually and then consider potential interactions. I'll start by examining the PDP for feature_A. A positive relationship means increasing feature_A values are associated with higher target variable values. This suggests predictive power. Next, I'll look at feature_B. A flat PDP indicates that changes in feature_B don't seem to strongly affect the target variable. Based on the positive slope of the PDP for feature_A, I can say that this is likely true because that positive relationship shows that feature_A strongly influences the prediction. That's a strong indicator. The flat PDP for feature_B suggests that feature_B probably has little to no effect on the target variable, making this a very likely outcome. That PDP is pretty flat. Because feature_B seems unimportant, removing it might improve the model. However, it's not guaranteed since other factors like model complexity or overfitting could still play a role, so this is only plausible but not certain. It's worth a try. I'm analyzing how much each feature in a model influences the outcome. Think of it as figuring out which ingredients in a recipe have the biggest impact on the final dish's taste. I see a flat line in the plot for this feature. This means that changing feature B's value doesn't really change the predicted outcome. It's like adding salt to a dish. If you add a little or a lot, it doesn't affect the taste much. The plot for this feature shows a clear upward slope. This tells me that increases in feature A directly lead to increases in the predicted outcome. It's like adding more sugar to your coffee, the sweeter it gets. I'm using a tool called _partial_dependence from the Sklearn library, a popular Python machine learning package, to examine how two features, feature_A and feature_B, relate to my outcome variable in a regression model, a model that predicts a continuous value. The plot for feature_A shows a clear upward trend, a positive correlation. However, feature_B shows virtually no relationship. Its plot is flat. Think of this as investigating which factors influence a plant's height. We are determining if moisture, feature A, and sunlight, feature B, are important factors in plant growth. I'm analyzing how much each feature influences the target variable using partial dependence plots, PDPs. PDPs show how changing a single feature affects predictions, ignoring other features. This problem is about interpreting those plots. It's like seeing the individual effect of each ingredient in a recipe. I'm using a popular machine learning library called Sklearn to understand how feature_A and feature_B affect my target variable in a regression model. PDPs show me the relationship. Feature_A shows a strong positive relationship, but feature_B shows none. The question tests my understanding of what this means. The key is interpreting the visual information from these plots. Because feature_A shows a clear positive relationship in its PDP, I conclude it's a strong predictor of the target variable. The plot shows it clearly, so it's an easy conclusion. Since feature_B's PDP is flat, I conclude it has little to no predictive power on its own. A flat line means no relationship. While possible, a strong interaction is unlikely. Simple PDPs don't show interaction effects. They only show the independent effect of each feature. I need more sophisticated analysis to determine interactions. Removing feature_B might improve the model, given its lack of individual predictive power. However, it's not guaranteed. There could be subtle effects not visible in the simple PDP. It's a reasonable guess but not a sure thing. I'm interpreting the partial dependence plots, PDPs. A sloped line in a PDP indicates a relationship between a feature and the target, while a flat line suggests no relationship. The slope of the line tells me the story. I see a question about figuring out how important different features are in a model using partial dependence plots, PDPs. We'll use PDPs to understand which features are strongly related to the target variable and which are not. The key here is to connect the visual information from the plots to the predictive power of the features. It's like detective work. We're given a scenario where I'm using a machine learning tool called Sklearn to make partial dependence plots. The plots show how two features, feature_A and feature_B, influence the outcome, target. Feature_A has a clear positive relationship with the target. Higher feature_ values lead to higher target values, but feature_B shows no clear relationship, it's flat. Based on this visual evidence, I need to decide which statements are most likely true. Importantly, I'm told to assume the model is good and there is no serious relationship between the two features. Let's look at what the PDPs tell us. A partial dependence plot, PDP, shows how much a feature influences the target variable on average. A positive slope means a positive relationship. Higher feature values usually mean higher target values. A flat line means there's no significant relationship. I'll use this information to figure out the answer. The PDP for feature_A shows a clear positive relationship. This means as feature_A increases, the target variable also tends to increase. That is a strong indicator that feature_A is a good predictor of the target. The PDP for feature_B is flat. This strongly suggests that feature_B doesn't have much impact on the target. Its values don't seem to influence the target variable consistently. I'm analyzing partial dependence plots, which show how features influence a target variable in a regression model. I'm focusing on two features, feature_A and feature_B. The goal is to figure out which features are important predictors. It's like detective work, looking for clues about what drives the target variable. I'm using a tool called _partial_dependence from the Sklearn library to visualize how two features, feature_A and feature_B, affect the output of my regression model. The plot for feature_A shows a clear upward trend, meaning as feature_A increases, so does the target variable. But the plot for feature_B is flat, suggesting no relationship with the target variable. Multicollinearity is avoided, which means that there is no correlation between my features. Based on this, I need to choose the most likely true statements about the predictive power of these features. The positive relationship in the plot tells me that feature_A is a strong predictor. As feature_A goes up, the target variable goes up. It's a clear and strong signal. The flat partial dependence plot for feature_B means it's not a good predictor. There is little to no relationship between feature_B and the target variable. The plot shows no consistent change in the target variable as feature_B changes. Because feature_B seems to be useless for prediction, removing it might improve my model's performance. It's a good candidate for removal, but there's a slight chance that it plays a small role that is not visible in the plot. I might need to investigate more to be sure. I'm analyzing partial dependence plots, PDPs, which are visual tools showing how a single feature influences a model's predictions, ignoring other features. They're really useful for understanding feature importance. I'm looking at a specific question about how two features affect the target variable in a regression model. I'll use PDPs to figure out which feature is the more important predictor. The PDP for feature_A shows a positive relationship. This means as feature_A increases, so do the model's predictions. It's a clear sign that feature_A is important. The PDP for feature_B is flat. This tells me that changes in feature_B don't seem to affect the predictions much. Feature_B's predictive power seems weak or non-existent. Based on the positive relationship in the PDP, I conclude that feature_A is indeed a strong predictor. The flat PDP for feature_B strongly suggests it has very little predictive power. Removing feature_B might improve the model, especially if it's adding noise, but it's not guaranteed. It depends on other things like how complex the model is. A strong interaction is unlikely because single-feature PDPs don't show interactions. The flat PDP for feature underscore B doesn't eliminate the possibility of interaction, but it makes it less likely. I'm presenting a situation where we use a technique called partial dependence plots, PDP, from the scikit-learn library to understand how features in a model affect the outcome. Specifically, we're looking at two features, feature underscore A and feature underscore B. The partial dependence plot for feature underscore A shows a clear upward trend. This means that as the value of feature underscore A increases, the predicted value of the target variable also tends to increase. It indicates a strong positive relationship. The partial dependence plot for feature underscore B is basically a flat line. This tells me that changes in feature underscore B don't seem to significantly affect the target variable. In other words, feature underscore B doesn't seem to be a good predictor on its own. We're going to use the information from the partial dependence plots to answer a multiple choice question. This question tests your understanding of how to interpret these plots. Based on the upward sloping PDP for feature underscore A, I can confidently say that feature underscore A is a strong predictor of the target variable. The flat PDP for feature underscore B strongly suggests that it has very little to no predictive power for the target variable. While interaction effects are possible, we are given that there's no strong multicollinearity, reducing the likelihood of this being true based on just the single feature PDPs. Since feature underscore B shows little predictive power, removing it might improve the model's performance, but there's no guarantee. It could be a case of overfitting, or feature underscore B might have subtle effects unseen in the PDP. It depends on other factors. This whole exercise centers around understanding and interpreting partial dependence plots, PDPs. PDPs are a valuable tool for understanding how features impact predictions in a machine learning model.